and out. Even the non-drowsy. Yeah, even the non-drowsy ones make me drowsy. Okay. So you have project 4 due today, which technically it must be due Thursday, April 27th. I won't grade them until I get done with the 280 exams, and that's actually my biggest class. Got like 35 students in there. We're going to talk about RERAM today. We'll start CMOS imagers next week. We'll do that for 3 or 4 days. We may do a final exam review. Your final exam is optional. If you're happy with your grade in here and you've turned in your course evaluation receipt, of course, you don't have to take the final.
I wasn't thinking very much when I got my first COVID shot. 4 weeks from then is Thursday, April 29th.
Okay.
So I would get my second COVID shot just before this exam. So I'll probably take up the optional part.
Yeah, you can, if you like your grade, you don't have to take the final. Usually I have maybe like 2 or 3 people actually take the final. Yeah, you just have to sit, when you get done with your course evals, hit the button that says notify instructor, and I get an email saying you finished it. It doesn't say what you said about me, it just says you finished it. The notify instructor is usually good enough. You'll get an email back from me that basically just says, I checked you off. Okay, let's kill that. Where are we at? Plans for the summer. Edmund Blackadder, you should watch this show. Great insults. How to avoid work I don't want to do is by working full-time in the lab and get more work, because I am getting more work because I'm actually going to be there this fall. So I've got my own projects now. 2 of them, by the way. You couldn't just leave me with 1. It's quantum stuff, so I'll be okay. So this is resistive RAM. I may, okay, the antihistamines, okay, on top of that, I spent most of last summer looking at ways to use RERAM that don't involve memory, and a lot of quantum mechanical effects. So some of this I may just start babbling. And these slides were written back when I was mainly trying to just do the readout, do an analog read on a memory device. Our first idea for the puff, not everybody in here knows what a puff is. A puff is a physically unclonable function. And this is kind of the hardware end of the lab. And what we're trying to do is we're trying to take standard parts that you'd find in a normal computer system and read them out in ways they were not meant to be read out. So we're hacking into them and doing analog reads, figuring out ways to do analog reads on digital devices. Or other things, whatever we can come up with that will produce some kind of analog read. There are defects going from device to device, like in a memory cell. Not big defects that cause it not to work, but little defects that cause it to be slightly non-uniform.
Does that relate to the term puff?
Physically unclonable function. I'll get there eventually. Okay. Puffs. Because I have to talk about puffs, because otherwise none of this that I could say about RERAM would make any sense. So some of the things we've used as puffs, you can build like an FPGA and build a bunch of ring oscillators in it. And all the ring oscillators will have slightly different speeds, and you can compare the speeds of them and use it to generate a random bit that we use for encryption keys. We just need to be able to read the randomness in the devices. I figured out a way to get random data out of a DRAM by through a lot of shenanigans. I had to hack into the chip. If you're really interested, I won't tell you today, but come to my office hours or something. Basically, to be able to say which one of the DRAM cells decays faster, pick any two at random, which one decays fastest, that is the one that I call a 1. And I know predictably it's going to do the same thing every time I power it up. I pick a different DRAM chip, it's going to have a different pattern. Different pieces are going to be different. And this is how we're using ReRAM. We actually use it before it's formed, and we measure the resistance of the devices and compare them. And why it has been. So that's kind of the background. Now let's talk about ReRAM, how it works in the real world. What? Yeah, there's a whole bunch of different ways we can do it. We could read out one cell and say, is it above a certain resistance or is it below a certain resistance, and call one a 1 and call one a 0. We could compare two cells and do kind of like the arbiter puff, like from 639.
You can't do an arbiter puff very efficiently on FPGA because issues.
Every time it powers down, you have a different puff. That's the biggest issue. Don't touch that mouse. Okay. Somebody else is here. Luke. Okay. All right. So if I'm a little fuzzy, I use ReRAM a lot, but if I'm a little fuzzy on how we actually use ReRAM as memory, that's why. It's been a while since we tried to use ReRAM as memory and make a puff out of it.
It's funny to think about that.
But we don't use memory for remembering things at all. I really hacked into the Micron chips, but after teaching this class, I could do that. Okay, so there's a lot of things we say here that seem like they're fairly easy to do, but they're a lot harder in practice. You know, like for MRAM, we said we just need a material whose magnetoresistance goes down with temperature. Please give it to us and give it to us with these characteristics. There's a lot of work that went into it. Let's just build magnetic circuits on top of the CMOS. It should be easy. A lot of work went into that. So there's a lot of things that you assume other people can do easily, they actually can't. Be careful with that. This is a hysteresis curve, and we saw these in Dr. Cambo's lecture. Basically with ReRAM, we're using internal redox reactions, and recall from chemistry, a redox reaction is a reaction where charge is interchanged. So you're creating ions that are either positively charged and negatively charged. And if you have a whole stream of negatively charged ions, you got a path for current to flow. So that's basically what they're doing. They start out with something that looks like a capacitor. It is literally, this is the basic ReRAM cell from an engineering viewpoint. The physicists think this is amazingly simplistic, but I like it. I've got a metal, and I've got some kind of oxide. To me, that looks like a capacitor. It is a capacitor, and yeah, it does have capacitance associated with it. And that was another thing I proved last summer, that the capacitance doesn't matter. Because the way my linear model of this device, and I'm the only person I know that's actually ever done this, looks like this. It's a resistor in parallel with a capacitor. The resistance is really big and the capacitor is really small. And if you go through and do the 280 linear equations thing, where you write the differential equations, take the Laplace transform, solve them, un-Laplace transform them, it basically comes out the time constant associated with this is so small that, and our measurement time is so big The only thing that really matters is the resistance. Now I'm talking about memory as non-memory.
And that's where the regram comes in.
Yeah, but
And then so the oxide, let's see. So
it's pristine. And when they first build these devices, they don't put channels in there for current to conduct. We're actually going to physically damage them to get current to conduct through them and to become useful devices. But we damage them delicately.
hurt them softly.
We hurt them softly. Okay. When I'm programming ReRAM, you saw this hysteresis curve, but I'm going to explain it in a way, not just drawing the little loop around here endlessly. See, it works. I know you guys don't know what hysteresis is, unless you took maybe some power classes. So in the off state, I have a resistance that looks like this. It's got a very small slope. A small slope, since this is I versus V, means a big R, and maybe that's like 500K. Now, if I program it, I'm going to take the voltage across the device all the way up to V set. And when I get it up to V set, depending upon how much voltage and how much current I'm limiting it at, I can get this up into one of these other curves. And so once it's in one of these other curves and I turn V set off, it's going to go back down to this point, but it's going to be operating along this curve. So when I measure the resistance, the I over V, I'm going to get a big slope. I get a small R. So the difference in resistance of the device is what's going to, what we're going to measure as being a 1 or a 0. Now it's going to stay in this state because it's locked in this state until we take the voltage negative. And when we take the voltage negative all the way back to V reset, then we can get back on this part of the curve where it's off. So a positive voltage to program a 1, a large positive voltage to program a 1, a large negative voltage to program a 0. And once it's stored, we're only going to read it like in this region where we avoid both setting and resetting. Okay. Now, when I first started in the lab, I was just I don't know what they thought my job was going to be.
When you were
When I was a pup engineer in the lab. I think I was supposed to just be the FAP, the friendly adult presence, just to make sure the kids didn't screw up anything. There's a couple of postdocs in there. One was doing FPGA design and one was doing analog design. And I pretty much knew more than the analog designer, so I ended up doing some of that work. And then both of them they were postdocs, both of them got real jobs and moved on and are doing really well right now. And then I started kind of doing the analog design for a while, and then I started doing some of the theory and making up projects of my own. And now I'm a grad student.
Now you're a grad student, and you took 310s, and I do that.
No, I hired an FP. I did my usual thing. Oh, you're okay. So my entire life, I've like 5, 6, I don't know how many times. Okay, Julie, it's time for you to learn FPGA design. Okay, I'll do that. And I start to learn it and I get semi-confident at it. And then I realize, hey, I'm not going to ever be great at this. It might be a good idea if I just hire an FPGA designer. I guess how this ended this semester. I hired an FPGA designer, and I'm going to be working with him. I'm going to be like sketching out the circuits and telling him on block diagram level how it works. He can do the details of the programming, not me. So I was doing analog design at that point in the lab, pretty much. We wanted to be able to read these things out at 100 nanosecond, 100 nanoamps. So 100 nanoamps times 100K is only 10 millivolts. And 100 nanoamps times 50K is only 50 millivolts. So we basically programmed the current, read the voltage, and used the magic of Ohm's law to calculate the resistance. The problem was getting the accuracy. They're very small signals. They're close to 0 volts. So we needed things like, to get good linearity at 0 volts, we know from 380, you need a negative power supply because you're hitting close to that power supply rail. So I needed to design a low noise negative power supply that could run off of something from an Arduino at that point. I needed a amplifier front end with a resolution of 25 microvolts. That's gotten a little bit better now. That supply but I just bought parts. I went to Analog Devices and I picked out the right parts and strung them together and it worked. 100 oh, this was the doozy, and this has never been actually done. The 100 nanoamp current source needs 1% compliance, which means it can only go between 99 nanoamps and 101 nanoamps between an output resistance range of 1K to 10 megohm, which means I need to get the output resistance of this thing around a gigaohm. I've theoretically built some really beautiful circuits, and I've been doing this like it's once a year. This is Julie's job to start the summer, is to build this current source. And after about 3 or 4 days, they decide it's not a priority. So I've made a lot of headway on it, but I haven't actually built it yet. No, it's oh, you can't use big resistors because they're noisy. And you have to use FETs. Actually, the best thing I had was BJTs. So there's a lot of things going on here that seem simple from a physicist standpoint, but tend to drive the analog designer crazy. And analog designer usually defaults to me because I'm the one who knows the most about it. I'm trying to train somebody to do this.
Analog designer, right. This is crazy.
Well, we all drive each other crazy. So when you're working, you're not going to be working just with a team of electrical engineers. More than likely, there'll be mechanical engineers. And well, with me, it was mechanical engineers, optical engineers, physicists, geologists, astrogeologists, etc. And we all had our own little separate lingos. I was the one who could translate between them. So this is pretty much the sense amp. I ended up designing for this ReRAM starting out. What I had here, and this was in the early days, this isn't exactly what we're doing now. I had a reference resistor, and I basically just switched between a bunch of different values here. So this is a fixed value for the measurement. I have my ReRAM connection was going through another multiplexer right there, and I was supplying the same current to both of them. And I had to supply the same current to them, whether this was 1 k ohm or 10 megohms. We narrowed that down a little bit. Me and Raul got that to work. I found a really good instrumentation amp here that could handle and just had sensitivity down to 25 microvolts to tell which one was the bigger resistor. And if this one was bigger, I called it a 1. If this one was bigger, I called it a 0. But this had to operate off of a plus and minus supply. So my digital signal out of this thing was plus or minus 2.5 volts. So I put this comparator in here and was comparing it to ground, and basically had a level shifter on there. And that worked fairly well for about a year or two. And then Dr. Cambeau came in and changed all the rules. And so now somebody else is designing it. We were trying to figure out how to read this puff and what we were going to read as a puff in those early days. Now we kind of know what we're doing, or so we think, until it changes again. Yep, he's allowed to do that. Here's the power supply, and I came up just this week. I just threw this whole thing out and said, start over again. I had a switching converter here, but we know switching power supplies, charge pumps are really noisy to generate the plus and minus 2.5 volts, so I could have good linearity at those low voltages. And then I found a really low quiescent current positive and negative regulator, which I put on that to regulate the noisy supply from the switching converter. Nobody had integrated this into a chip, and I thought it was a crazy idea, but it would probably work, and it does. And then just this week, I go and I look at analog because the guys in the lab are having trouble getting this to work because it involves them soldering. The package is really weird. Soldering to a really weird package. And I find that Linear, which is now owned by Analog Devices, has built one chip that has both a switching positive and negative converter in it and a linear regulator, all integrated together. So I just told the guy to use that. You got to go back and check these things every 2 or 3 years. People go out, well, sometimes more than that. One part, and it will work. Okay, back to ReRAM. Silver film. This is a silver filament. There's different materials they make it out of, but the idea is basically the same. I've got this MIM structure, which means metal insulator metal, which electrical engineer in me reads as capacitor. I is a resistive. It's very highly resistive. It's like an oxide. It's like a capacitance. It's a really highly resistive region, almost capacitive, and conducting electrodes. The reason why it's not completely capacitive, and it does have some resistance to it. What happened? Oh, nobody's moving over there. Okay. It's okay. The reason why it's not completely capacitive is that this is a really thin oxide. It's like 1 to 2 nanometers. It's almost like that flash thing where if you put enough energy across it, electrons tunnel through. And then it's a thin enough oxide, you can do that. And this is what I wasted most of my last summer doing, was calculating theorizing about the different mechanisms that were causing this. So, the little yellow thing. Okay, so it's different. I've got silver ions here. I've got one, and these are going to be other types of ions, or what they do. What Sandia does is we were working with, who was sending us samples last year because they had a bunch of stuff left over, is one side had tantalum and the other side had tantalum oxide, and the other side had tantalum oxide with oxygen deficiencies. So not quite, the ratio of tantalum to oxide was different, so that there was less oxygen in there, which made one side slightly more conductive than the other, which meant these things had a polarity to them. There was a direction that current would prefer to flow in them. Now, if you're using them for puffs, I don't make the filaments.
No filaments.
We avoid the filaments at all costs, and that's what I was trying to do, is figure out what it took to avoid filament formation. Most of the literature said that filaments form when you get a high enough voltage, a high enough electric field across there. I did some, me and Sean,
Sean Robbins?
Yeah, me and Sean Robbins did a whole bunch of measurements that basically blew that theory out of the water and said that what's really going on is it's energy. It's not electric field. It is, electric field is like voltage with a fixed thickness. It was voltage, it was current, and it was time. So if you actually write an equation for energy and you integrate it with the electric field being constant, the current being constant, what you get is energy equals voltage times current times time. So if I raise the voltage too high, too much energy, they'd blow. I'd form a filament. Too much current, it would form a filament. If I put a really low energy, really low power, really low voltage and current, and I sat there and let it go for a really long time, it would blow. form a filament. And once you form a filament, you can never unform a filament. So this is where we're using them. For puffs, we're using the MIM structure. Now, if you want to use them for memory, you form those filaments on purpose. I have to create this initial filament on here. It takes a larger amount of energy to create the initial filament than it does to actually program it and deprogram it. So all of these go through an electroforming cycle. That's generally done by the manufacturer, unless you tell them not to, which we do. Don't do that, they'll break it for us. We create this initial filament. If I want to get a low resistance device, I put a voltage across here that's going to cause this filament to get bigger. I know I'm not frozen. And the resistance to go down. If I want to make the filament smaller, I put the voltage across it in a negative direction. I swap my VDD and ground electrodes. And once I do that, I make those all go away. And I go back to that pristine state. And I get two different forms of memory. And then again, back in the early days of the lab, and still it occasionally pops its ugly head, we have this thing called trits. If you've taken 638 or 639, you've heard the word trit.
I have heard, but I don't think I've ever explained what they are.
What is a trit? The Air Force just went through and did these calculations to find out what was the optimal base for computing. You know, we use base 2 computing. It's bits.
Oh, yes.
Zeros and ones. And so the Air Force did this curve and they found out the optimal number of states per device, which would be a trit. Well, it actually came out to be 2.7. It was amazingly close to E. And 3 was the closest number to that. So they want to build this trit computing structure. Turns out we've used this concept. What?
So,
Use 2.7. You're like, oh, this is a 1, and
Base E. Well, that's kind of what we do with trits. What we do is it plus minus an X or 0, 1, and X. We have 3-state logic. Believe it or not, we're actually using that, and I'm building quantum trits next fall. Or over the summer. Yeah, there is 0, 1, and I couldn't measure it.
There's some sort of joke here that
There's gotta be. But yeah, but with ReRAM, we could actually do the same thing we did with Flash, and we could potentially program 4 resistance states into the cell and make it like an MLC, be 2 bits for one actual device. And now I gotta move you guys over to the other side of the room. So after electroforming, which is the initial state, a lot of times done in the factory, what I'm gonna do if I wanna program it, I either apply a voltage pulse and limit the current. This is called the compliance current. It's the maximum current I can allow it to have because we don't want it to get too much energy into the device. So I apply V-right, or I could apply a current and limit the voltage. And this will, if I put it up at this voltage up at V set at the right current, I'm going to program an on, and this is also called set, or it's programmed. I'm going to get a low voltage on the output, and generally that can be like a 1 or a 0 depending upon how you define it. If I want to erase that cell, I'm going to apply a negative V-right or a negative current. I swap the polarity of the 2 electrodes, and I will program this down here now to be reset, and I can get back to that low resistance state. Right, and we talked about the next thing. How much time have I eaten? I'm doing better than I thought I would, considering the antihistamines. The tree pollen forecast for tomorrow is miraculously low, considering where it's at today.
So I'm not feeling well.
It's like through the roof today and yesterday. Yeah. Okay, so what we want is we want the right voltage to be in the range of hundreds of millivolts to a few volts, so it's compatible with 1.2, 0.8 volt logic. Flash really, it fails badly here. So we've got an improvement over flash, and you can do that. We want T-right to be fairly small, like on the order of 30 nanoseconds. And the reason why they pick 30 nanoseconds is because that's where DRAM's at. So if I can make it about the same speed of DRAM and lower voltages than flash, and it's non-volatile, I can have like that one memory to rule them all. What was it? Dr. Cambo was saying that too, but he was much different way.
About what?
The universal memory.
Yeah.
He had the pyramid.
Mm-hmm. Yeah, the pyramid that was just, I don't know, something about that pyramid just upset me a little bit.
Well, the pyramid was the pyramid of how fast the memory was.
Mm-hmm.
So we had like SRAM and cache, SRAM. We wanted to replace SRAM, cache, DRAM, and flash. Probably he had pretty much given up on hard drives because they're just used to store things for the next 10,000 years. Okay.
I think it's time capsules, but
yeah,
had a hard drive in it.
Yeah. And I just call it.
If you did that like 20 years ago with a floppy disk, you'd never be able to read it anymore.
You would have. Oh.
It means you just have to dig up something that you can read it with.
Yeah.
Go find a floppy drive reader. Huh?
Yeah. Okay.
Like, something that reads floppy disks in the actual room.
This isn't complete.
Really?
This isn't completely random. This is based upon a conversation that's going on in the room. I had this friend, Don Dunn. It was like the grand poobah best camera designer in the entire world. He designed the science cameras for the Mars rovers.
Oh.
And he was like right across the hall from me. His wife was a programmer, and she was a pack rat. She saved copies of every operating system she ever worked on and hardware necessary to use these operating systems. And she just had filing cabinets full of this stuff, right? And I'm sure there were people who were telling her to throw it out. But what happened is Y2K.
Oh.
And suddenly these banks and these healthcare systems and these critical networks said, hey, we've got this legacy system here and no one has COBOL version 3.2. Anyone got a copy of COBOL version 3.2?
She did.
She cleaned up. They retired after Y2K and bought a bed and breakfast in Vermont and happily retired.
I think you told me that story.
Probably. Don Dunn. Oh, I miss him.
But yeah, no, let's make a time capsule with like a.
Okay. So old memories. Sometimes being a pack rat is good, but I get rid of all that stuff.
I got
Floppies, any whatever. Okay. So back to real memories. T-right, we want to keep it comparable with DRAM, so we can compare. If we can do that, if we could make it as fast as SRAM, we could replace the cache with ReRAM. ReRAM can get integrated into a processor. I don't know if you caught that on Dr. Cambo's slides, but he was talking about them integrating ReRAM into FPGAs because ReRAM can take the heat. DRAM does not like being next to microprocessors because its performance goes down considerably when it gets warm.
So ReRAM is our savior.
ReRAM is one of our potential one memory to rule them all, to fill in the pyramid of memory.
We can throw it into a volcano and it's not doom and it won't be destroyed.
Maybe not that far. Ben wants to throw into a volcano. Okay. The minimum time that ReRAM's been demonstrated for reading at is 300 picoseconds. This is, and generally SRAM's around 1 nanoseconds, which is 1,000 picoseconds. This is as good as bulky, power-hungry SRAM. If we could get it that close in production, we would have the one memory to rule them all, or fill in the pyramid, whichever way you want to say it. Yeah, we need to put a ring around the pyramid.
Oh no.
So generally, the requirements are based upon what its competition is and what it's got to beat. We want, well, this is more basic. VRead needs to be smaller than VWrite, so we don't have those read disturbs and those write disturbs like you see in Flash. If I'm keeping this reading voltage much smaller than the writing voltage, I'm going to prevent unintentional writing. And the hysteresis curve is pretty strong. I have to get up over that V set before I start actually writing to it.
That photo just outclasses Flash right there, doesn't it?
Yes, it does. Yeah, and Flash is horrible. I mean, it breaks down all the time. And this is why you have the garbage collecting part of the controller for Flash is basically to go through and pick out which blocks have such a high error rate that we're not going to use them anymore. And this is part of the reason too, if you've ever had a flash drive, if you've ever managed to hang on to one of these little remote flash drives for any length of time, every time you plug it in, like over the years, the amount of memory capacity this device has keeps shrinking.
Yeah.
This is bad block management. Another thing is we don't want to make VRead so small that it can't be measured. And this would be the analog designer or the person designing the sense amp inside the chip. We want to keep it above like 10% of VWrite, hopefully above 100 millivolts. Designing analog readouts below 100 millivolts gets to be a lot trickier. We want to keep the read current above 100 nanoamps because we got to have enough to charge the bit line capacitance rapidly, and also smaller current sources are harder to build. We want the read time to be approximately equal to the write time so we can have bragging rights on those specifications. We don't want it to be like Flash, where the write time is microseconds and the read time is like nanoseconds effectively, because we just dump out a whole block at a time. Okay, the resistance ratio. Again, we don't want to have to design super sensitive sense amps or readouts if you're the one unfortunate enough to have to do this on the board. We want R off over R on to be roughly on the order of 10 or greater to allow for small and efficient sense amps, especially at low powers. It makes it a lot harder. And the ratio may need to be larger to account for bit line and other undesired resistances, especially if you're trying to interface this onto a board and you've got a trace and you've got to add that in there too and make sure your traces are all equal length and all that good stuff. Fortunately, we don't have to make it perfect. We have to make it good enough for a demo, and then other professionals come in. We're a lab. We're not Sony. That was the worst thing that happened to me at JPL. We have this perfectly manicured engineering playpen designed for us to just be able to go off and do what we want to do. And when it gets to be good, we hand it off to the Mars guys, who I just called the Martians. Hand it off to Don Dunn, let him build the camera, make it all perfect. And
Sounds like Don Dunn has his own little kingdom.
yeah, he did. Well, he had been there oh, he had been there forever. But he wanted to be, he's one of those guys who, he was a real techie guy. He wanted to do technical stuff. So he stayed in the lab. And there are a lot of people who like moved up, who worked with him that moved up through management. He also worked, he was there when the guy who was the director of JPL started out in the lab. So Don wanted to just, you know, stay there and do the techie stuff. So he did. He liked building cameras, and I was another camera designer who actually built cameras. Almost, I won't say as good as David. Well, I don't know. My cameras were not going to Mars. My cameras were going to the top of Mauna Kea. We're going to telescopes. Mine were ground-based astronomy, but they were probably equally as good. So we had a lot of fun talking to each other, going back and forth. Well, what was the point of this?
We were talking about Flash, and somehow we got back on
Flash, yeah, Flash is slow. Okay, so for endurance, Flash typically can endure between 10 to the 3, which is 1,000, and 10 to the 7th, which is 10 million write cycles. 10,000 cycles is perfectly typical. As long as ReRAM can beat that, we're okay, and there's not any problems there. It seems like that's working okay with the endurance.
Easy mode ReRAM.
Yeah, that was an easy one to beat. Memory has to be retained at 85 degrees C. That's the top of the automotive range. So you can use it in like automotive, high temperature industrial electronics. That's not really a problem, because to tell you the truth, oh well, yeah, when I was studying it over the summer, I found out that when you're actually forming this is kind of interesting. It's interesting to me. When you're forming this, what happens is you're forcing a current through here, and the current's going through a very narrow filament. So the current density, the amps per nanometer squared, is really high. And since the current density is high, where the current's flowing, it actually gets really hot. You get I²R heating. And the temperature inside that filament can get up to like 3,000 Kelvin. Right, and so it's enough to melt the ceramic, melt this tantalum oxide, and cause the ions to actually move around. So the ceramic gets melty, and the ions can move. Yeah. If you put your thumb on the hose, does it get warm?
No.
Okay, well, this is enough to actually make it, we would burn your thumb.
Yeah.
Yeah, okay.
Yeah, 85C is pretty hot.
Well, 85, no, it's operating temperature.
Well,
Yeah.
85C.
Yeah, this is like, 3,000 Kelvin, you might as well just call it 3,000 C. It is hotter than the inside of your oven, but it's just locally.
3,000 C is hotter than my oven.
I don't know, it's actually
It's hotter than your kiln. Wait, I don't know. Yeah, it is. It's hotter than kiln temperatures.
Yeah, kiln temperatures are like.
It's hot enough to melt ceramic.
And I need to have tungsten.
Okay. Okay.
It's like 5,000 C.
Yeah, I don't know. Okay, it's not enough to melt tungsten, is what we've decided here in class.
They have uraniums too.
Yeah.
I don't know.
Let's find out.
Look in the, Google it. I was going to say get out the CRC, and then nobody uses that anymore. It's called Google. Okay.
Let's see.
Okay.
Uranium's 1,132 C.
Okay. It's self-melting. Okay, sorry. Let's try to get back to. It heats itself up. Why do we got? Okay, never mind. We have to be able to keep the memory in its present state, even if I have a constant state of repulses. This was the read disturb we talked about in Flash. We don't want read disturb. If we read it a whole bunch of times, we want it to maintain its memory. Flash typically is spec'd at a retention time of about 10 years. Hard drives are a little bit better than that. So the goal for ReRAM is to have a retention time of greater than 10 years. So this is it. Don't drive the physicists crazy. How would we measure this? No, what you do is you do accelerated life testing. You put them in an oven, you do things that would, you put them in a kiln. You do things that would tend to cause them to age earlier, and then you estimate what the time it would be. You have it so it ages in a month, and you do horrible things to it to make it age in a month as much as it would age in 10 years. Stress testing. It's called accelerated lifetime testing. You'll hear that phrase at some point in your lifetime.
Just learn the good old uranium kiln.
Store them in the uranium kiln. I'm sorry, this whole conversation doesn't make sense without hearing there are people in here talking to me and inducing me to say things like this. I'm talking to the imaginary voices on the side. The voices in my head are named Zach and Ben. Now we're getting back into like spring semester. So, good. Now I'm not muted. Am I? No, I'm good. Okay. So electroforming is that initial process of forming a channel. I have to put higher currents in here to form this initial filament. We want it to be high enough so a very thin filament forms. And this picture is for silver, but tantalum, I keep saying tantalum because Sandia uses tantalum. No, tantalum oxide. I know what they use. ASU uses hafnium oxide. And Crossbar uses whatever secret sauce they use. They're not talking about it.
Sauce oxide.
Yeah, sauce oxide. We want the current voltage time. So remember, it takes energy, which is current times voltage times time, if we're putting a constant voltage and current in, to be high enough so that a very thin filament forms. If the filament is too large, I can't unform it. So this has to be done under very controlled circumstances, and it's usually done, the initial forming is usually done by the manufacturer. Right. The width can be measured by measuring the resistance of the memory cell. So you can do just like we did with Flash. Remember that read verify algorithm, where we kept increasing the energy we put in until we got the resistance we wanted. They're probably doing that in the factory under controlled circumstances. They don't care how long it takes to do this forming cycle. It's not going to affect the read and write speed. A few seconds and a few volts is usually sufficient. Yes, we found that out. That's what Sean and I were messing around with last summer. We use current compliance. Now, this is something Dr. Cambeau talked about that it's for some reason students don't understand this when they first come to the lab, is what we have is we have a big, this huge SMU. That's the word I'm looking for. And what it does is we have these ReRAM cells, and it's a very precisely controlled current source and slash voltage source. And we set this thing up. We typically set it up for like 100 nanoamps or so, or 100 nanoamps. But we put this condition on it, and this is called the compliance. and our compliance is like 0.5 volt. And what that means is it's going to pump 100 nanoamps through this circuitry with very high precision. No matter what resistance it is, it has the, I mean, it's a big piece of instrumentation. It will, it's capable of doing this across 10 gigaohms to 1K without any trouble. We put 100 nanoamps through there, and we say if the voltage goes up above, if the voltage tries to go up above 0.5 volts, I clamp the voltage at 0.5 volts and I drop the current. So it's actually doing both of these things. 100 nanoamps, the voltage is free unless the voltage gets to 0.5 volt, and then the current drops. Typically, it's we like to use a 0.5 volt mainly because most of the people tell us that if we get above 0.6 volts, we will form. We will start to form. I don't believe that. I believe it's power or energy. Sorry, because I measured that. and the guys at Sandia actually believe me on that. They just never looked at it that way before. We want the electroforming to ideally leave behind a single filament, which can be grown and shrunk to change the resistance of the device. Sometimes it leaves behind multiple filaments. You just can't, it just leaves behind filaments. Ways to check this, again, you take the devices, you slice them, you look at them underneath, you look at the cross sections underneath an electron microscope, and you're pretty much done. Wow, I ate up way more time with this than I thought I would, mainly because we were talking about uranium kilns. So yeah, basically, yeah, I don't know that. But we can, I could try. We got 3 regions in here, and what I know what Sandia does is they have one region right here. It's designed so that current generally flows in one direction. So one of this has like oxygen vacancies that wants the oxygen from the thallium oxide side, so the current off wants to flow in that direction. And these are in the middle between here. I put a region where both ions can flow and electrons can flow. Now, ions are atoms, remember, from chemistry. If ions are flowing, that means atoms are moving. It's gotten hot enough for the thing to get melty enough that the atoms can actually move around. And that you want to confine that to one region so that we don't accidentally get ions in these regions. Since we can, the only thing we can, thank you. Oh no, no, never mind. I thought somebody was actually asking me a question. If you think about it, we have electrons flowing in this direction. The only region where I can undo the damage and reverse it is in here, is in this ion flow region. So that's the oxide. Okay, good enough. We want a non-destructive readout. Yeah, we only want. Yeah, I don't know what I forgot what the point of this was. Non-destructive readout, right. The read operation cannot change the state of the matter. We don't want those read disturbs and write disturbs. I think I've already talked about this. We want the ionic current, the current of the ions moving, to be negligible during the read operation. And we want only of the states on only, I think there should be the word one in here. Only one of the states can actually be thermodynamically stable. The other's metastable. It will be stable until we make it non-stable by putting reverse voltages across it.
Stable until we say it's not allowed to be stable.
Right, so there may be some endurance issues with that. Yeah, and this is more chemistry type of stuff. And ReRAM, both of these may be metastable. So this is a problem for the physicist. We'll just say make it stable. And I think this was it. Any questions about memory or not, or using memory as non-memory? What? Or no uranium tailings? Okay.
You can't count.
Oh, I thought you said tailings. I was thinking of the tailings stuff. Grandpa was a rock hound. He used to like to play in the tailings dumps. You go down to Globe. You'd have the big pile of rock that they threw away. That wasn't what they were mining for, and he would like just go through their tailings dumps, which was the leftovers from the mine, and look for interesting things that he wanted to pick up.
Neat uranium things.
Yeah, neat uranium. There's no uranium in Arizona. The uranium mines are in northern Saskatchewan. Even I know that.
Yeah.
Okay, so okay, let me check roll so you guys can leave and you don't have to put up with us. Stop. Let's see. Nolan, I don't see you. Isaiah. Okay, you're not here. And Shujuan, okay, he's asleep. Okay, you watch the video, send me an email, and I'll give you your points back. Otherwise, you can go unless you have questions.
Sounds like you're just trying to do a question.
What?
You're just gone.
Okay. So I'm going to stop recording.
You're gonna try to use words, but
You should share your 1-second one. So I
Okay.
can point out something.
Okay. Oh, okay.
It's that I need the window at the top.